Alright, sorry about that. 10 minutes and so last time we spent quite a bit of time looking at propagation of these pulses on transmission lines, understanding what happens when transmission lines are connected in parallel, what happens when they reflect, and hopefully this idea that what happens local in time versus steady state are very different things, and you need to keep that in mind. So a 50 ohm transmission line always looks like a 50 ohm transmission line at an instantaneous moment, even if it is connected with has different lengths or has different terminations on the right. Sorry, I need to play this. Right, so the difference between local in time response versus steady state response and what happens to things with transmission. Phase changes at different interfaces, so sorry, with different ratios of impedances. So if the load is less than 50 ohms, then you get a sign change. The load is not is higher than 50 ohms, then you won't get a sign change on reflection. Okay. And usually, if there's a setup which involves reflections, but your source is matched, so whatever wave will come back to the source will never go back again. So that part of the things we can ignore in such analysis. Now, this kind of situation is not really seen that much in a practical sense. It's more for illustrating the concepts and also to understand what one should not do when one is connecting high frequency signals with coaxial cables. So the very specific thing being about using those T junctions. Right? Now at low frequencies, people still use them. If you're working at kilohertz, makes absolutely no difference. But the impedance ideas will still play a role. So at very low frequencies, the idea of even because you will not be concerned with time scales of nanoseconds, right? If you're talking about kilohertz, then you are, the time period is milliseconds. So you're not going to be concerned about. So this whole local in time concept can be just forgotten. Steady state and local becomes the same thing because you will not have a long enough line to worry about the time it takes for the signal to propagate to some boundary condition and come back. So that aspect doesn't play a role. So if you connect things in parallel, it's okay, but you have to keep in mind that whatever is the load impedance at the ends will then determine if you're, what is going to be the voltage drop at a particular point. So in that limit, the transmission line really just plays the role of two wires. You can just forget about its characteristic impedance and things like that. Because essentially, if you connect something at one end and there is something else at the other end, the presence of that other load is felt instantaneously, again, within quotes, because the time scales involved are typically much larger. So if you connect a short circuit at the other end, you will feel a short circuit here, and your circuit will respond accordingly. So, so that scenario is really more for illustrating purposes and what not to do. You will rarely encounter such situations unless you're debugging. You set something up and you're seeing on your oscilloscope like a ghost image of the pulse you sent, then it means that somewhere along the line there's a problem and it's reflecting. And you can use this idea to actually estimate where the problem might be, because from the time difference, you know the distance where the problem has to. Right? If you see a reflected pulse, like a small pulse like we were seeing, showing up about a couple of nanoseconds later, you know you don't have to look for problems very close to the circuit. It has to be at least that time into speed of light in the coaxial line, which is not the same as free space. Usually it's about a factor of 3 smaller in typical transmission line coaxial lines. You have to check that. Okay. So today we will move on, discuss different types of coaxial lines. Forgot to click on this message off. So we will look at a few different types of transmission lines which are commonly used. On Friday, you saw examples of what we call the SMA cable. Actually, the SMA name is associated with the connector and not with the cable. The cables are usually associated with the dimensions of their outer diameter. So the thinner coaxial cable I showed you and set up most of the things on Friday is a 085 cable. So 085 here means 85 mil, which is milli-inch, 0.085 inches. That's the diameter of the cable. And the cables I had brought there were actually a combination of copper, the one which was sort of brownish in color, and there was maybe one which was silvery in color. That is just tin-plated copper. That just helps soldering to that metal a lot easier, because your solder is made of tin, lead tin solder, so it's easier to solder to something that's tin-plated. Copper tends to get corroded over time, so you have to clean it in order to get a good contact. But they are both, the active metal is basically copper, so in terms of conductivity and other properties which will determine the losses are going to be that of copper. Tin might have a small coat. Sometimes the center pin is made of again has some coating to reduce losses. And we also saw a fatter one, which I called as the BNC cable, but that again, the BNC refers to the actual connector, and the cable itself has names. I think that one might have been called some RG, some number. It's again goes connects to the diameter, the dimensions, and those are usually made out of braid type of material. It's not a solid metal. It's braided, so in that way it doesn't have as good a shielding property as a solid metal shield. So the ground plane, the ground of the coax also acts like a shield for your.
So what's the difference if we have like a Faraday cage poles and an actual box? Shouldn't they work together?
Sorry, say that again. A Faraday cage.
Like you are saying that it is coaxial and it's made of plastic, but they are shielding it. They are in contact. So shouldn't a solid piece and a threaded piece act?
Oh, you mean why there is a difference in the shielding properties between the two? So because the shield is never perfect. It has gaps in it. So
but
it's not
going
going
are in contact. So if wires are in contact, so there's no problem. That's what the Faraday cage is like. So when we build a Faraday cage, don't need to be like it makes holes are there, but it doesn't.
Okay, let's discuss this for a little bit. It's off topic, but it's a general lab concept. Let's make a Faraday cage, which is like a box. You want to shield it as well. You're saying holes are okay. How big a hole can I make? Can I make the hole as big, almost as big as the size of the box, and it's still okay? So what determines that? Exactly. So it depends on the frequency. So if you have a sheet of metal as part of one wall of the Faraday cage and there is a hole in it, it's a very small hole, then basically electromagnetic waves below a certain frequency will only couple evanescently into the thing and back. But below a certain above a certain frequency, which is basically set by the diameter of that, you can have wave propagation through the hole. So that is essentially the idea. So it works well at low frequency. That's exactly the reason why they are made like this, cheaper to make, and it works well at very low frequencies. But if you are working at high frequency, then those holes have to be smaller and smaller. So then you just go to a solid shield, it's just better. But this shielding aspect of the cable is a side aspect. The primary purpose of the outside outside metal is to provide the ground for the coaxial cable. So the comment about the shielding was just an added thing. So, and again, remember that these are single-ended signals, right? So they can pick up noise in other ways as well. So there are also varieties of cables which look like a BNC cable, but actually the center is two wires twisted. So the signal is actually being carried between those two twisted wires, and there is still an overall outside ground. It's called a triaxial cable, triads, and they have their own special connector. So if you're working at low frequencies and you care about your wires not picking up.
Okay, so in high frequency range it matters.
Yeah, matters. So this, so similarly, in fact, I mean, since we started this point, this actually has a practical impact on certain type of experiments we do, even though we have not conclusively proven that yet. Because we work at experiments at 10 millikelvin, and we use superconductors in our experiments. I mean, I don't know, you probably have not been formally introduced to superconductivity, but basically the superconducting state is protected by an energy gap, which is basically the energy that is required to break the Cooper pairs which are responsible for superconducting transport. And for us, having everything being completely dissipation free in the superconductors is very crucial. And one has to worry about sources which can provide enough energy to break these Cooper pairs. And the material we use is aluminum that only has a transition temperature of around 1 Kelvin. So this, if you now turn that into an energy, so the transition temperature is connected to the energy gap. So if you turn that energy gap into a frequency, then we are talking about 10 to 20 gigahertz and above. Now, turns out that because your cryogenic environment doesn't only contain the lowest temperature stage, it has higher temperature stages as well. And every temperature stage is radiating at its temperature. Now, you might not consider a 1 Kelvin plate to be radiating heat because we think of that as being cold. But when everything else around it's colder, then the heat, the black body radiation that is emitted from those hot plates or hotter plates actually has a finite photon flux at those frequencies. It's small, but it's enough for it to break Cooper pairs in the experiment. So a lot of the groups, we used to use these flexible cables, which I showed you. This was the other cable which had this blue covering, and that was SMA type, but it was flexible. So it's not a solid shield. And people have noticed that if you use them at the cryogenic stage, even though they're fine electrically, their shield is not good enough to prevent these, tens and 100 gigahertz kind of radiation from getting in to the cable and then into your device. I mean, and we are talking about like fractions, a very, very tiny amount of power and like few photons or a few tens of photons. But remember, photon energy is very small, so even a very tiny power can have lots of photons. So we recently put a solid aluminum tape around it, and we have seen some improvement. But this was one trial, so we don't know whether it actually improved it. But I know many other groups which advise against using these flexible cables. And over time, they also get damaged. The shield of that cable gets damaged and frayed, so it can then leak more RF energy. So definitely you can test this, that if you have two coaxial cables which are very close to each other, you might get crosstalk, very small crosstalk, but it will still be there if you use a braided cable versus maybe a good thing we can try at a later stage in class as a demonstration to see how that works. So we're talking about extremely fine points here, but these things can make a difference. Yeah.
So there are two things, right? You're saying the outer photons might come inside our cable or the power leaking out.
No, I'm worried about coming in. Power leaking out is not a problem because it's very small anyway. The problem is that because power will leak out at the frequencies at which you are operating, which is still a few gigahertz. It's not very big. So the leakage outside is going to be insignificant from the point of view of losing power, which you're actually sending in or coupling to a nearby cable and doing that. That's insignificant. The frequencies we are talking about is now close to 100 gigahertz. So it's much beyond the frequencies we are interested in actually doing the experiment. But 100 gigahertz radiation entering your cable and then traveling down the cable actually as a TE mode and not as a TEM mode, because the cutoff frequency for the coax below that. Then it can get into your sample box and just spray your sample with this kind of radiation. So that's the problem. So there, even a very tiny amount of coupling is bad because they will break Cooper pairs and then give rise to dissipative transport. So what happens then is that you now have a combination of Cooper pairs and regular unpaired electrons, and those will dissipate energy like they do always. So one has to worry about that. Okay, so we will do a combination of things. I will introduce you to these different transmission lines, how they are defined in terms of the dimensions. We will look at some of their properties using microwave office software. There are some tools there which allow you to calculate properties about these transmission lines. And then I'll also show some physical models which one can use in microwave office to look at these things. So these are not what I call finite element simulations, but these are pre-solved models for that particular structure. But now, instead of specifying an electrical length and the frequency, we're actually specifying all dimensions. So the length of the transmission line, the dielectric, what is the gap between the wires, depending on the geometry. And then I'll show you how to use those things. So that's your cross section of a coaxial transmission line, which is what we have been mostly discussing so far. You have a center pin of radius A, and that is usually a solid cylinder, if you want to think about it like that. And then you have an outer cylinder, which is hollow and of radius B. In terms of electrical transport, you know that currents usually flow on the surface of the metal, right? So the thickness of the outside shield, because it's a hollow cylinder, in some sense doesn't matter so much unless it becomes so thin that it starts to affect the resistance per unit length of that particular material. So usually the outside, it's the thickness doesn't play a role in the properties of the system. So what's the relevant thickness?
The skin depth.
Right? So if as long as your metal is thicker than the skin depth, it's not going to propagate in those regions. So then you're good.
Talking about the surface resistance.
Yeah. So of the outside metal, right now of the outside, I'll come to the inside part. This is just to explain which dimensions mentioned here are important for the purpose of a transmission line and why others are not relevant, not shown here. Now the center one is a solid, usually. It can be hollow, but it cannot be hollow from cross-sectional side, in the sense that you cannot have this surface also be hollow, because then you actually have a tube or as well, which can support its own modes, right? If there is a gap there. But from the point of view of the transmission line, it's still the outer surface. So one could have a tube, but remember that it's much smaller, so it will have a cutoff frequency which is much higher. So that will not support a TEM mode. So from the point of view of the coaxial line, it's the outer surface of this inner conductor and the inner surface of the outer conductor, which are sort of the relevant boundaries you have to worry about. Okay. But the way they're usually constructed, it's solid on the center pin is solid for practical reasons.
So the center pin is hollow. So there will be TM or TE modes.
Yes, that's right. That's what I said, that TEM modes won't be present inside that smaller tube. But one could imagine a scenario where you could now have nested coaxial cables, one inside the other. The reason I'm just saying is that we were thinking about this for some research project a while back. You could completely have another coax, which is composed of the inside one of the outer legs. Basically, this now becomes the outer conductor, and there's another center pin here. And there could be two independent TEM modes, one which propagates between this surface and that surface, and another one which propagates between this surface and this surface. And if the intermediate metal, which is basically this boundary here, so this boundary, is thick enough, then these two don't see each other. Right? So you can have a transmission line inside a transmission line. Right?
What would be the advantage of making such a regulation?
Well, this was something very specific. There's no advantage. So one obvious advantage is that you can now have multiple signals propagating on the same length of the line, right? But it will be very complicated to launch and extract the signal out of this kind of a geometry.
So we are putting the outer surface on ground. Why can't we have the inner? Is there some difficulty where it is?
Well, so the ground reference usually is arbitrary in this case, but usually the ground reference is given to the terminal which has, let me say how to put this correctly. In some sense, the lower impedance or resistance, because it's a much bigger surface. If you now really talk about ground as when this is interfacing to a circuit, it's a lot easier to access the outside than the inside. Like how do you take that and connect it to ground? So here, that's why the convention is that the outside is basically ground. There are transmission lines where there are no grounds, because all the models you saw till now actually does not distinguish between the two conductors, right? The telegraphers models we saw for the ground. There's really no distinction between the ground is just a reference. You can equally define the ground on the other side, and it wouldn't really matter. If you have drawn your model symmetrically, so that would mean that we do this kind of. So remember, your model had L's and then C's to ground, right? This was not really considered as another metal. But if you want to do that, So if you want to draw that transmission line symmetrically, you have to draw it something like that. Then the two sides are equal. But usually, because in most cases where there is a ground definition, you will see that that conductor will be much bigger than the other conductor. So in coaxial, the center conductor is thinner, and the outer conductor is has a larger surface area. So if you think about what would be the inductance of a section going this way for the outside shield versus for the inside shield, the inductance will be larger for the inner one because it's thinner. Okay. So that makes it a natural way to define the outside ground. So it's not just a matter of convenience for that matter, because what would you be looking for as you go from one point to another point in the transmission line is how the voltage is changing, right? So if you just look at the ground surface, you're not going to see anything changing along the transmission line. Everything is going to happen on the center conductor with respect to the ground for the voltage. But for the currents, you're going to see changes in the center line. So usually the geometry defines one to be naturally ground in all cases of transmission lines which are asymmetric in their structure, like the coaxial and like others we will see today. And then I'll also show you examples where the ground doesn't exist. There it's perfectly symmetric. It's like a differential signal. So anyway, so this coax inside the coax is again a digression. But point is that the relevant surfaces that we clean this up again are the inside surface of the outside conductor and the outside surface inside the conductor for the coaxial line. So which means the only dimensions which then matter are the radius of the both cylinders. Actually, it's the radius of the inside and outside, because what matters is actually the gap between the two. So you will see how that enters in the expressions. And then finally, what will matter is what's filled here. It's air or is it a dielectric, because that will affect the capacitance between the center pin and the outside. Usually in any regular coaxial cable, there will be some dielectric, because you can't have an inside conductor just floating in free space. However, for smaller sections, like connectors, I was telling you on Friday that connectors are also the small sections of transmission line, but of a different geometry and created in such a way that they can adapt to a smaller cable transmission line to a bigger diameter, because those are easier to work with. Some of the high quality, high frequency ones and the low loss versions of these things can mostly be composed of air as a dielectric, with only very thin, small sort of stands, holders, which keep the structure in place, made out of a dielectric. So it's again within the transmission line itself of that connector, you're going to have different parts having different properties in terms of the construction, but everything has to be 50 ohms, otherwise you'll get reflections. So those connectors also tend to be a lot more fragile, because it's like the center thing is now being held together by some very thin dielectrics at two ends, and if you push it too much, you can actually break the connector. So we will look at connectors at a later stage. So this basically tells you that the radius, inside radius A, outside radius B, and the epsilon r of the dielectric is basically what's going to tell you the properties of the transmission line. Right? The conductivity will also play a role, but we are going to be always working in the low loss regimes. So from the point of view of characteristic impedance and velocity of propagation, it's only C0 or L per unit length and C per unit length which matters for computing the properties of the transmission line. So to give you the Z naught and to give you the phase velocity of the waves. So want to show you this page. So earlier in chapter 2, they let's see this one. They basically give you these formulas for computing the L and the C, which is inductance and capacitance per unit length, but also the resistance and the conductance. And these come from equations like these here. So you can take a look at this yourself. We are not going to be interested in deriving these things in much detail. But essentially, the idea is to equate expressions for energy in terms of the field, and then writing them in terms of this inductance per unit length kind of argument and equating the two. Right? That's basically what it's going to tell you what this quantity inductance per unit length is. So you and what this expression will give you will depend on the expressions for what H is and what E is, right? And this will come from the description of these things as TEM modes. For a cylindrical geometry, you want to go into a cylindrical coordinate system, and that will give you the correct Maxwell's equations and put in the boundary condition. So that's actually discussed both in this part of the chapter and also in chapter 3 where we were looking at. But essentially, you compute the magnetic part of the energy and equate it to Li square over 4. Again, these are all per unit energy in a small section. And then from that, you can get these kind of expressions for the coaxial line. So now let's just get this. The resistance and G is not so important, but you see that P over A, it's always entered as a ratio. Right? It doesn't even matter what B absolutely is, but what A absolutely is. It's the ratio, which basically means it's the gap. Right? It's not really the gap because it's not the difference, but it's the ratio. But that's because that tells you the spacing between the two conductors. So inductance per unit length is proportional, of course, to there's a factor of mu here, permittivity, but it basically goes as log of P over A. Now, is it surprising that you have mu showing up here and epsilon showing up here?
Electric fields and magnetic fields.
Depending on the identity you use.
So, I mean, already here in these definitions, you have mu's and epsilon showing up because the energy density is going to have three factors which are related to that. But these are inductance and capacitance per unit length. And if you look at it, it's this mu, it's just some prefactor which is dimensionless. Okay. Because remember, we discussed that mu has the same units as inductance per unit length, and epsilon has the units of capacitance per unit length. And in connection with free space, so when you sort of push this to the limit of free space, these become basically mu naught and epsilon naught. So these geometric factors, especially if this was a coaxial cable with no dielectric, it was free space, then this would be just mu naught. Now, in most cases, mu is always mu naught because we are not working with magnetic materials, and only dielectric constant will come in. Relative permeability is always going to be 1 for most cases. So these are essentially geometric factors. So what you will see later on also that for the formulas for different kinds of transmission lines, basically it will be mu into some prefactor. That prefactor depends on the geometry and the materials used for epsilon, for example. So it's log of B over A. So remember, B is the outside diameter and A is the inside diameter. Okay. So if you just look at the trends, what does it mean? For a given A, if I increase B, so that means center rod is fixed and I'm just increasing the outside diameter, the inductance per unit length goes up. Okay. Now, that's kind of not so easy to understand intuitively. So let's look at the other case, which is if A becomes smaller, then inductance per unit length goes up. And if A becomes bigger, it goes down. Now that is consistent with our initial intuition, saying that a thinner wire will have more inductance. So it's just in some sense, it's an extension of the DC idea, even though it's not probably the most correct way of thinking about it, that if you have a thicker wire, it has less impedance to current flow because it has lower resistance for in this direction. So similarly for inductance also, if you have a thicker wire, it's going to have lower inductance. So if you ignore the outside dimension for the moment, because we are saying that that's sort of the ground part of it, but the inductance will become larger if the center pin is thinner, and vice versa. Okay. Now, let's come back to the other one we started with. This part is a little bit subtle, but it is related to mutual inductances. It's actually the connection between the two conductors. Why? By increasing B, the inductance goes up. It's basically a shielding effect, which is now becoming less effective. So one way to think about it is that if you have like a metallic ground plane, and at some height edge, you have a wire. So I've sort of cut the coaxial cable and made it into a flat thing. The inductance of this wire actually depends on whether another piece of metal is coming close to it or not. If this was completely removed and it was just a wire, it will have the highest inductance per unit length. As you bring this other metal closer, it induces currents flowing in the opposite direction in the bottom. And that effectively, you can think of this as that it gives a mutual inductance effect, which cancels the L in this main line. So that's the reason why making B bigger makes the inductance also go up. So it's a shielding effect of the presence of the second conductor. Gaurav, did you have a question? The capacitance part is easy to understand because it's just simple parallel plate kind of argument, right? So B over A being large means more gap between the two conductors. So capacitance per unit length goes down. And if they are closer to each other, capacitance per unit length goes up. But the logarithm factor really comes from the cylindrical geometry of the system. It's kind of strange to think. You would think that for the capacitance, because it really is like a parallel plate capacitor, right? Except just that it's wrapped around itself. Because the distance between the two is always the same. So you would think it should just be proportional to the, it actually should have just been equal to the distance. But maybe in some sense it is because log B over A is like log B minus log A, I guess. So it's, but in terms of which direction the capacitance increases and decreases is obvious from here. So you can now figure out if you have a fixed outside dimension, how the inductance per unit length and capacitance per unit length change depending on the center diameter of the coaxial. Now, usually coaxial systems are not constructed like as a custom thing in a lab, because you buy these cables and everything is 50 ohms. So that ratio is already sort of fixed depending on the dielectric they are using, and that dielectric is also usually fixed. It's usually a Teflon based dielectric called PTFE. If I remember correctly, I think it has a dielectric constant of 3, and the those ratios are fixed. There's not much. Now, if you're building some custom structure inside your lab, or as later on we will see that small sections of transmission lines can be used as resonators because they have boundary conditions that causes waves to go back and forth, and that can set up resonances. Then you might construct them in a custom fashion. So later on, I will show you an example of such a structure made in our lab. It's not really a coax, but sort of looks like a coaxial cable. So just to summarize, the connection between a geometry and the inductance per unit length and capacitance unit length basically comes by connecting the idea of electromagnetic energy flowing present in a section of a transmission line computed from the fields, for which you need to solve the Maxwell's equations for a particular geometry, and then equating it to the telegrapher's model of the transmission line and writing it as Li square and C square. And then from the equating those two, you will get these numbers as and C's. They will always look like mu into some prefactor and epsilon into some prefactor, which are geometry dependent. The exact variation of those parameters on the dimensions will be very specific to the geometry. For the case of the coax, this goes as a log.
So,
Yeah.
The
what?
capacitance per unit,
What about it?
whether increasing the
Oh, so if you look at this structure here, this is one metal and this is another metal, right? If I sort of cut it and I spread it out, then this just looks like two pieces of metal at some. In fact, I should really open both the things and lay them out flat. So it really looks like a parallel plate capacitor, right? So for a parallel plate capacitor, you know that the capacitance basically depends on the distance between the plates. So here in this geometry, if you want a smaller distance between the plates, then that means B over A has to be close to 1. And if you want a larger distance, then B over A has to be larger than 1. So that's basically what's showing up here, that the capacitance is going as 1 over log B over A, which means for large B over A, separation is large, which means lower capacitance because the plates are further apart, and vice versa. Doesn't explain why there is a log. I'm just talking about trends. The log actually comes from the fact that it's a cylindrical geometry. You have to look at these two equations. Sorry, not this one. This one, and you equate that to CV square.
Then in a quarter line, whether we have to increase the inductance or increase the capacitance, but both will scale oppositely.
Yeah, so that depends on what you want with your coaxial line. So it's entirely up to you. But that's what I was saying, that practically speaking, you just buy these coaxial lines. You don't make them in-house unless you're making some small sections for very specific purposes. So it really depends on what you want for your characteristic impedance, because L over C is what matters. So if you look at the ratio L over C, it will go as log B over A squared. And then there's a square root, so that will go away. So, even Z naught is going to basically be proportional to log B over A. So you decide, depending on what Z naught you want, you choose the B and A accordingly. But there are infinite choices, right? Just like we know that there are infinite choices for L and C to get the same L over C. But what will change is then the velocity of propagation of signals on that coaxial line. So if you go to the limit with large L and large C, then the velocity will be slow. If you go to the limit with small l and small c, then it will be faster. And as L and C become smaller and smaller, ultimately you hit the limit of free space propagation. In fact, I think for coax with an air dielectric, the velocity is that of free space. I have to double check, but I think that's
But how A1C increase simultaneously? Because for increasing L, we have to increase B.
Yeah.
And for increasing C, we have to decrease B.
But you also have A now. You have both of them. So if you only increase, change one dimension. So let's say you fix outside dimension and you decrease the inner dimension. That's going to give you more inductance and less capacitance, which means your characteristic impedance will go up. L will go up. So if I do, if I decrease A, this would mean L would go up, C would go down, and that would mean Z0 will go up, and vice versa. If I increase B, then that implies L will go up, C will go down, and again Z0 will go up. So if you want to make coaxial cables which are of different dimensions overall scale and still have 50 ohm transmission line, you have to adjust both A and B. So if I go from a thin coax to a thicker coax, then both A and B have to be changed in order to maintain the 50 ohm transmission. But that's going to be true for most cases. So let me now show you this tool. So in microwave office, so here for this tool, we actually don't need to make any circuits. So in the tools menu, there is this thing called a TX line. It's basically a small tool for computing these numbers. So the example we just saw, which gives you the formula. So once you have that formula, you can compute the characteristic impedance for any coaxial dimensions. Right? So you have these kind of formulas fed into various tools, so you can compute these directly. So here there are various types of transmission lines. So we start with this round coaxial one. So it gives you the specifications in terms of what dielectric you want. It has given some standard set of dielectrics. So let's try air. And it gives you different metals. So these again only affect the losses. So this also computes the loss for you. I'll show you how. So you can just leave that for now. Sometimes you can actually just specify the conductivity as well. That's what changes as I go from say copper to silver. This number changes. So sometimes we, because in our lab, we often work with superconducting materials, and there's no specification. I just make this conductivity some very large number so that it doesn't affect the loss part of air volume. So, because it can have a very small effect on your characteristic appearances if you're not in the lowest one. So, anyway, this is one of that important. There is also this specification called loss tangent, which I'm sure you have heard. It's got to do with the losses in the dielectric. Those are the two ways losses can enter into your transmission line through the conductivity, finite conductivity of the metal, and due to the finite loss tangent. So the loss tangent part is what usually shows up as the G, because that's the loss in the capacitance part of your circuit. Since I put air, there's no, it's basically assuming this as a vacuum.
So to change the viewport from.
Sorry?
That equipment lab part, could we remove from?
Oh, it's fine. I'm here on keyboard. That is standard. See, this is way to. Zooming. Maybe you can just, why don't you come up here?
So there's
Oh, something happened. Oh, okay. Wait. Magnify. Huh? No, that has happened because of this magnifier. I am the one who's moving, but like I have to look at different one cursor and there's a enlarged cursor. Manage this. It's gone. So this keeps studying. So let's go.
What you could do is open the magnifier again, and there's a view option here where you can follow the cursor to the magnifying glass for this.
I don't even know where how that magnifying.
Just type it in search magnifier.
Oh, it came from Windows.
Yeah.
What is the view?
So
Views, folders.
should be something that follows the cursor. Maybe text.
You know, this is not very useful. I can't type. Good.
Maybe it is not.
It's fine. Whoever wants to see can stop close by. Okay, so dielectric we want to use copper. And, yeah, so basically, this tools allows you to compute in both directions, which means that I can specify the dimensions and see what the properties are, or I can specify the properties and it will tell you which, what are the dimensions you need. Of course, the inverse calculation is a more complicated thing because it has search in the space. So sometimes if you don't enter things properly, it will just get messed up. So let's try to set the numbers to, so you see, this actually provides that unit milli, which is milli-inch. So if I now enter 85, which is the standard coaxial cable I was telling you about, and we also set this. This one that's inch. Say it's 10-inch cable. So physical length again doesn't matter for the characteristic impedance calculation. It actually only affects this thing, electrical length. So it actually tells you that if you make a physical line, how long it needs to be physically for a particular electrical length to obtain at that specified frequency. So that's why the frequency number is here as well. So if I now, okay, so right now I don't know what the center diameter is, so I can't go to 20. Let's choose 6 gigahertz as a reference frequency. These things we can ignore. And I click this button, and it gives me this, that the characteristic impedance is 62 ohms. The electrical length is 1830 degrees. So you see that if I now make this length 100 times longer, the only thing that will change is the electrical length. So there's an extra 0 there. Just trying to make sure that the length doesn't play a role. By the way, this is the diameter, which is this, not the radius. 085 is the diameter. So it's 62 ohms. Obviously, it's not a 50 ohm because the dielectric for those cables is not air. The standard cables, it's usually PPF, which for some reason they are not provided here as a standard. But let's see if I just increase the dielectric constant. So now we can see that the impedance is higher than 50 ohms. And that makes sense because we have removed the dielectric. It's now air dielectric, so it's lower capacitance per unit length, and hence Z is higher than 50 ohms. And 50 ohms is just because we know what the weight of cable is. So if I now increase this to 3, big compute, then it has become 6 ohms. Now, of course, I don't even know what the sector diameter also is for that. So maybe I have this number, but there you go. 3 is 20. This gives you 50 ohm transition. Electrical length, and it gives you loss as 1 dB per meter. So that tells you how much loss you will have per meter per unit length of the cable. Change the. So remember, log is dB is again a ratio of power in log 10 log ratio of power. That's the definition. So to go back to the thing you were asking, if I wanted to change the dimension, I have to change both. So if I go from 85 to say 100, but I want to retain 50 ohms, now this is going to make it 55. So I'll have to increase this so that it comes back. Okay, that was too much. So see that we have increased both of them. Some other numbers which are shown here, just wanted to explain. So electrical length, you of course now understand what it is. It's just now because it knows the physical length and the velocity, and that velocity is basically related to this phase constant because it's giving you that as degrees per meter. Right? So it's connected to the electrical length. Let's see if there's something in inch here. So you see degrees per inch is 316. Since this is a 10-inch cable, it will give you 300, the same thing multiplied by 10. It's the total electrical length. So if you wanted to make a quarter wave section of a transmission line of this type, then you have to choose this number so that you have something close to 90 degrees. So you could also do this where I can now enter 90 here, press the right arrow, and then it will tell me the correct arrow. So these tools are useful because when you're actually designing them, you can basically check from this what is the actual physical dimension. Disclaimer here is that these calculations are always somewhat approximate. You will find that when you actually make these things, there are always tolerance issues and other things which will give rise to some small variations, usually of a few percent in what we make here. Usually what we do is we start with this to get an estimate of the dimensions we need. And then we do a full electromagnetic simulation to confirm that it is as close as to the properties we want. And then we do tweaks for that. But it's a good starting point. It's also a nice tool which explains, allows you to sort of see how the different numbers change here. One other quantity here is this thing called effective dielectric constant. Now, I've never fully understood it, but it, I think, is an intermediate quantity in the calculations, the models they use, which tells you something about what is the dielectric which is actually to be considered in the system. Okay. So I have to explain this with an example, otherwise it will be confusing. So you see the effective dielectric constant here is 3, and the dielectric constant I have defined is also 3. So just to show you, if I change that, this will also be. So what does that mean? Why is there another thing called effective dielectric constant? The reason the two are the same here is that all the fields in a coaxial geometry are flowing through a region of space which is filled with the dielectric of this material, right? So in a coax, the inside space is fully filled with the dielectric, and the fields only exist there. They don't exist anywhere else. So that's the reason effective dielectric constant, as mentioned here, is the same as the actual dielectric constant.
So what changes in other geometries?
I'm sure. In other geometries, the fields will exist both in the dielectric and also in air. These are usually cases which are circuit board type of transmission lines. Okay. You'll see some examples just in a I'll go till 1 o'clock. Yeah. So what else? Yeah. So that's basically. So now, if you look at this loss per, maybe if I now change this from copper to silver, which has a slightly larger conductivity. So you see the losses have a little smaller. Silver is 6. Yeah, it's larger conductivity. So for silver, the loss per unit length is slightly smaller. If I make this really bad, 3, you see the loss per unit length is increased. None of the other things have changed. Now, at some point, this will probably throw up an error because you can't put very high losses. Now, it seems, yes.
So this model is working in that regime where we still say that L and C and everything else will be determined at characteristic. It is only if the alpha is determined by the finite. Like
yes, that's right. Low loss model, the one we okay. Now there are some other things you have to keep in mind. It's also of both of practical and also of specific to using this tool. What are the limits on these dimensions I can choose? Okay. We know that practically speaking, transmission line or coax has to be a certain geometry, but can I make this outer diameter like 10 times bigger than what it was and make this also 10 times bigger? That will ensure that log of B over A is still the same. Let's see if it computes something. and you see that it does compute something, but it gives this warning. What does it say? Outer diameter is greater than quarter wavelength. This is connected to the idea we were discussing on Friday of what is the difference between a thin coax and a thick coax. And remember I told you that it now depends on whether you can start fitting wavelengths in the other dimension. So you cannot have a gigantic coaxial cable and expect it to propagate in the same way at low frequencies, because you will now have these other modes. So remember, I was mentioning this at the beginning that there are these TE modes which will come up. I'll just show you the that part. Those are, so if you make everything very big, then all the higher modes which are far away, they will all come to lower and lower frequencies. And you want in the coax everything to be only, all the action to be happening along this direction, not in this direction. So things should not be varying. There should not be a phase difference between as you go along this dimension. But that basically means that there are other kinds of modes of propagations which will come in. So this kind of general idea of what these dimensions should be applies to all kinds of other types of transmission lines as well. Everything doesn't just scale continuously. Yeah.
So essentially, DNA changed the cutoff frequency, right?
Actually, mostly just B and A also to some extent.
What do you mean by quarter wave?
What do I mean by?
Quarter wave.
Oh, quarter wavelength, because that's sort of what they have determined as what is considered to be a long compared to wavelength. So if something becomes of the order of quarter wavelength, because that's sort of where we can say, okay, there's a node here and a node here. I mean, it's an arbitrary. You could have said that I should really not have the dimensions increase beyond 1/10 of the wavelength. So this quarter wavelength is just a cutoff they have kept as when the calculations are no longer going to be accurate. But you are right that maybe here a more accurate cutoff could be when the cutoff frequency of the TE mode comes within some percentage of the frequency you have specified here. So by the way, this is quarter wavelength at what frequency? At this frequency. So if I make this also 10 times smaller, it will stop suffering. Right? So in that sense, you can scale. If you want to make everything bigger, you bring your wavelengths also, make your wavelengths also bigger, then it's fine. It will behave like a nice coaxial line. But if you're working at 6 gigahertz, you cannot make a transmission line with these kind of dimensions. It won't work properly. You'll still propagate, it just won't have a well-defined characteristic in start exciting of the future. Okay. All right. So, so that's coax. To summarize, the field, one of the important points here is the field everywhere is going through the same dielectric kind of thing. And that's why this effective dielectric constant is same. So it has, just to add another point, it basically affects your capacitance per unit. If your field is not present only in the dielectric and also in, because energy will then be distributed differently, that will affect how you think about how the impedance and coming from the capacitance per unit length will change as you change the dielectric of the system. Because now the total dielectric is a combination of both the dielectric you're changing and air. Usually the other part is air, right, or vacuum. Right? So the I'll show you the cutoff frequency. So the next transmission line I want to discuss is the strip line. Okay. The strip line has a geometry which looks like this. There is a center conductor, which is this one where the mouse is. It has a certain width, a certain thickness. I will come to that thickness part just a bit. And there are two ground planes on either side, which are spaced by distance d. And it's assumed that the center part is right in the middle. So it's not like skewed towards one side or the other side. You can sort of see that this is an extension of the coax model itself. Right? If I now imagine I slit the cylinder, so iPad. There. So you have your coax, right? I cut it here and I cut it here. And then I sort of stretch it out. Cut it in the middle, the ground plane, stretch it out, put one part on the bottom and one part on the top. And then I change the center part to now look like a rectangle. That's one way of thinking about how you went from a coaxial line to a straight line. Just to understand the similarities between them. Remember the field lines for the coax we had discussed, the electric fields are radial and the magnetic fields are circular. The current is flowing in and out of the plane. Magnetic field circular. Both magnetic and electric fields are perpendicular to each other and perpendicular to the direction of propagation. So the strip line very closely reproduces that kind of an effect. So it also supports a TEM transmission line, TEM mode. These are usually used in circuit form because obviously this top and bottom ground plane are not extending to infinity, but they are slightly complicated in the sense that the center conductor is buried between two things. So if you're talking about something on a chip, it's not so easy to access the center conductor. But there are actually specific microwave devices where the strip line geometry is the only way to make them correctly. And that's got to do with the fact that the wave mode is the true TEM mode. So again, what are the relevant numbers here? The width, the gap, for the similar reasons to that of the coax. If I reduce the width, it's like a thinner center conductor. So inductance is going to go up. But at the same time, it also is one of the plates of the two parallel plate capacitors which are now happening between these two and these two plates. So there's capacitance now from both sides, right? There's a capacitance here, and because these two are both ground planes, we assume that they are at the same potential always. That is a important assumption. So if the center conductor becomes smaller in width, then the capacitance will also go down. So that means just changing the center pin, increase inductance. So reducing the center pin width increases inductance, decreases capacitance, which means Z naught will go up. Usually, the gaps, the B is fixed in a structure, so you only control the width of the central trace. That's the only thing. So if you want higher impedance, you have to make it smaller width. If you want smaller impedance, you have to make it larger width. So let's put some numbers in here. Electric constant of 3 is fine. Let's choose some more realistic kind of micron or maybe millimeter is a good unit. Again, the physical length only will affect the electrical length. So let's say a height of 1 millimeter, a width of 100 microns, thickness of 1 micron. I'll come to the thickness part in just a second. So what is the thickness? It's like this. Gives a warning. It says W over P recommended to be greater than 0.1. Basically, exactly 0.1. So this again is related to the model approximations under which these things are computed. You don't want the sector to be too small compared to the gap of probably to have more proper parallel plate kind of configuration. Gives you 87 ohms, so let us make it close to 50 ohms. So that we need quite a large quite the height on the bits somewhere close to 50 ohms. This is of course for dielectric 3. So it's higher than we need something. So let's, if I now make this 6, what will happen to the characteristic? So, go up or go down?
Capacitance will increase.
Capacitance
Capacitance will increase.
Yeah. So it's 36 ohms per. So this is now close to 50 ohms. I could also do this. Other part is also fairly straightforward to understand. If I now increase B, the gaps are going to increase. That means capacitance will come down, so impedance will go up. So if I now do that, this is the other way.
So we like about inductance. We must be controlling that as well.
Same way. So the same argument that the effect of the shielding, which I talked about, the top plates come close to the center pin, the inductance will go down. So if you just see how the formula for the straight line actually looks like. So now what about the thickness? So here, unlike the case of the coaxial thing where the thing was uniform, the thickness there only contributed to the loss, because as long as you're there, the skin depth really doesn't matter. If I now just say, let's say, go from 1 micron, so keep in mind the relative dimensions, right? This is 1 micron is much thinner than 300 microns for the width. So this is a very thin film. So right now the impedance is 50 and the loss is 0.098. So make it 2 microns. The loss increases or decreases. That's strange. Yeah, now it's behaving better. Usually, okay, maybe it was too thin. That's why it was behaving straight. Let's see 4, if I go to 10, loss is going down now, which is natural because of the overall thickness but at some point it will saturate. But it does have a small effect on the impedance as well. One part is actually just obvious because as you increase this thickness, the gap is coming down a little bit. Right? So that's one part of it, which will affect the overall. But mostly it's going to control the losses. So but typically for these kind of boards, I think the thickness of copper is about 35 microns. Losses now. So it's a very low number, something strange is happening. Maybe the calculation actually is just going wrong. It's not even giving the warning for that. So again, look at the effective dielectric constant. It's same as the specified thing because again, all the fields are in the same area, which is filled with the dielectric. So that's why here also the effective dielectric constant is same. So if we now shift to, I'll just quickly introduce 2 more transmission lines, but we will discuss that again in more detail in the next lecture. So there is this thing called coplanar waveguide or CPW. This has so there's a dielectric slab of height h. In all of these planar transmission lines, the dielectric is basically what's called the substrate. That's the holder of the entire circuit. Then you have a center trace of width W, thickness T. Thickness here again plays a similar role like last time. And it has 2 ground planes on either side, but horizontally, laterally, as opposed to the strip line which was up and down. So remember, strip line was like this. Now this is the center, and this is ground and ground. And now you have something like this: center plane and ground, ground. And there is now a gap between the ground and the center plane on both sides, and it's usually symmetric. So this gap and this gap are always made the same. So if you think about this, this is also one other way of transforming the coaxial line, where we have removed it from the 3rd dimension and put everything on the plane. So the advantage here is that all the terminals are now on the same plane. So from the point of view of interfacing this transmission line to other circuit elements, which could be some components or chips, which you are placing on the circuit board, it is easier because you have access to both the ground terminal and the center terminal. Whereas for the strip line, the center terminal is actually buried inside the ground plane. So it can be very tricky to access that. So this is called coplanar waveguide. Again, I just want to show one thing before we, because we're running out of time. There are some numbers already entered here. I'm just going to run the calculation for that. But all I wanted to point out is that now the effective dielectric constant is no longer the same as what is specified. The reason is now the field lines. So remember that this here is all dielectric. Okay, this has some epsilon r here, but this is air above. And the field lines are going to have both things going from the top and going to the bottom as well. How much of that will depend on the what is the dielectric constant, what is the spacing between those plates. So that will change. So if I, for example, change the gap to 20 microns instead of 10 microns, you see that the effective dielectric constant also changes slightly. It's a very small change, but you can see it just change. Because the field distribution depends on these dimensions as well. One of the really nice things about the CPW is that you can make very large CPWs and very small CPWs because it's the ratio of the width and the gap which determines the characteristic impedance. And that is very convenient because you can have very large transmission line CPWs which can interface with big connectors where you're bringing the signals in. But then you can make everything smaller, just like we're talking about the coax, both the center pin and the outside pin becoming smaller. You can make the CPW taper and become very small, with both the center and the gaps being small. And now it can interface with some devices you are doing experiments with. So it's very, very convenient for that aspect as well. But we will discuss this in more detail in the next class. There is one variation.
This whole structure is buried in a dielectric.
It's on top of a dielectric. So look at the figure here, this figure, right? So the dielectric is at the bottom and the metal is on the top. I have some information. Yeah. Pass these around. These are examples of CPW transmission lines. There are actually 4 of them coming, or maybe 6 of them.
Which part is true?
So this is it's like this. Okay, so this is the dielectric thickness of the substrate, and then the metal is basically 3 traces you're seeing here. That's the center, the 2 ground, and you can see the taper also happening here. It goes from a larger dimension to a smaller dimension. But if you look on the back side of that, you see that it has a metal. So there is a variation of CPW, which is called CPW ground. The only difference here that now there is a metal plate at the back as well. So this changes the capacitance per unit length and inductance per unit length because now the capacitance is between both the side ground planes and the bottom ground planes as well. Again, field lines are going to be present both in air and in dielectric. And this is actually the more common version which is used. The one I'm passing around is actually the type CPWG. And there is one important thing which again we will discuss in a lot more detail in the next lecture, which is that these ground planes, remember I told you that they have to be all at the same potential, at least at a particular location in transmission line. Otherwise, this whole argument breaks down and there are some other complications which can come in. And that is not obvious how you would do. So if you see that circuit board has lots of holes in it all along the line, I don't know if you noticed that. Those holes are actually short circuits from the top to the bottom. There's a coating of metal on those holes, which connects the top ground plane. So it basically connects this ground plane to this ground plane and then this ground plane to this ground plane, so that they are all now connected to each other and they form one continuous piece. So if you think about it, it now actually looks like half a coax. Right? So I have now, there is a ground here, there is a ground here. I've actually connected this ground to this ground. Maybe it's like a rectangular coax. So that's what a CPWG is really like, right? It's like a little bucket of ground plane and then there's a center pin in the middle. But this has to be done, and that requires one to those, they're called via holes. So that's C2WG, but I'm just quickly going through this, but to cover this again. Structure.
And one more question, so the previous one we saw the split and this one, these have like sharp edges. Usually sharp edges have high electric. So does this have any influence on the device or there's no problem?
You're talking about these kind of edges?
Yeah,
This
yeah,
edge?
yes.
Well, they are not, I mean, that sharp in the sense that when you physically make them, they will have some natural rounding off. What is your concern that?
Does it? I don't think it should change. The E-cross I think still be along the line. So it doesn't affect it.
It doesn't affect the overall transmission line
Like
structure.
in case of coax, it's like quite a round shape.
Oh, you mean because it's round?
Yeah. With round we don't have a problem, but when you restrict thing.
For example, one can make a coax which is sort of rectangular in shape. I can make the outer body like this and the center pin like this, and that's, you know, there's no problem. This also will support a TEM.
That's the purpose.
Yeah.
In terms of working at
So sharp edges can have other type of effects which are not directly related to the transmission line properties, and this is something we worry about in our research. It's about concentration of fields, and if there are lossy dielectric near that field, then it can increase the dissipation. But that's a whole different optimization we're worried about. But in terms of transmission line properties, this makes difference.
So when we start off, there are like four of them.
There are multiple transmission lines here, so there are actually
When you just-
6.
When you just start, there are like four.
Oh, you mean at these edges?
Yeah.
Okay, no, those are actually something else. They are where the connector is one which is connectorized. Pass that now. That's where it connects. So there's a little gap there. So those don't play any role in the actual propagation. So it's just cut there for making that clamping easy.
And these holes are for making sure that both the things are like
The holes which
straight
are
down.
going all along the line. And by the way, I mean, I guess if you're seeing them for the first time, you're orient. There are 6 transmission lines here. Like they're all coming from the edges and going towards the middle. So some of them share the same ground plane, but that's okay. Every alternate one, the middle ground plane is the same, but you're not going to have fields going much beyond the edges. So there's going to be no fields here you have to worry about. So that one is basically this kind of a board, but with the connector clamped onto it, so that now you can go from coaxial onto the chip. So the last one is the microstrip, which has only one ground plane and one center conductor on top. So this is like a strip line with the top half removed, both in terms of the ground plane and also the dielectric. Okay. And again, one point here I want to show for now is that the effective dielectric constant again is not the same, because there are going to be field lines both above and below the dielectric. And here is an example of lots of microstrip transmission lines propagated. I'll tell you about this structure later, but if you follow it from the edge, it's just a center, it's just the center pin, which is changing dimensions, but it's just going around in various ways. And those circles are actually, they give rise to interference of waves. That actually does a very specific microwave structure job, which we'll study about later. Okay. This is the most commonly used transmission line, the microstrip, even though it does not support a true TEM wave. It actually supports a quasi-TEM wave, but it doesn't make a huge difference in the sense that the main effect of that is a frequency dispersion, but it's small enough that it doesn't matter.
So
You can make it.
this is the lower part.
That's the ground plane. Yeah.
And the holes are again for the same.
There are no holes.
Like not along with it.
No, those holes are again for the connector, not for, there's no ground stitching going on here.
That anyway should be on the metal connector.
Yes, but here there is no grounds which have to be connected. There's only one ground. So this is convenient because there's only one trace which is going, but it's not so convenient if you want to connect something between the center pin and the ground plane, because now the ground plane is buried. So microstrip is sort of like CPWG without the side ground planes, or it's like the strip line without the top half. So there are, these all can arrive at them from different angles. But in terms of making simple sections, if you don't have any components which have to be attached to the thing, but you're only making like resonators or sections of transmission line, then microstrip is quite a convenient way to do it, because there's only one. That's only because once you buy that board, that thickness of this thickness edge is fixed. Then the only thing you have control is on the width. So again, larger the width, higher the capacitance, lower the inductance, and hence lower impedance, and vice versa. That's the only thing you have to control to get your transmission lines. So in that thing you're looking at, you see there are lines which are changing in dimension, and they are done for very specific. Some of them are quarter wave transformers. The actual device which is made here is something called a rat race hybrid, which is something we'll study later on.
So that the design has like a sub parts of.
Yeah, it has many things going on here.
There is a nut.
Yeah. Yeah, so it starts as just a 50 ohm transmission line feeding in, and it changes impedance for actually some kind of an impedance transformation. Then it goes into this circular thing, which is actually the job of that is to split a signal into two in a specific way. Okay, all right. So I think that's a good place to stop. In the next lecture, we will continue with looking at the microstrip, the strip line, and the CPW in a lot more detail, and then move on from there.